Yes, yes, testing, one, two, testing. All right, good morning to everyone. Sorry for the wait. I forgot to bring my iPad to go and get it. Um, Hopefully you are preparing for your presentation. If you have any problem, let me know. Maybe on Friday, I want the leaders to report to me what's your progress. Okay, on Friday. And on Friday as well, we will discuss your midterm. Okay, so please ask your friends to come. Okay, so you can check your midterm score. Okay, please come, yeah. Don't message me afterwards. You want to get your score. So we'll discuss the result, discuss the solution, so that you can check what's your mistake, what stuff you missed. Okay. We are really close to the end of the semester already, so we are left with the last chapter, differential equation. I'm not sure how long we're gonna spend on it, but definitely less than 4 lectures. So I have posted the revision question for you to do. Okay, so you can start try and do it. And after finishing chapter 9, we could do revision question, or you can send some question on the forum, send to me, and we can do it together in class. Or if there's some other ideas or section that you want me to go through more thoroughly, then you can let me know. And we can go through it again. All right. So then let's start our last chapter on differential equation. All right. So I claim that you already see differential equation before. Okay. So maybe let me ask you a question here. Let fx be a function. That satisfies function of fx. You come across this kind of function after you differentiate, you get back your stuff. E to the x exponential function. Oh, okay. So in particular, fx equals to e to x will have the corresponding. So in this section here, we will look at derivative in terms of itself. Okay, in terms of itself. So last time, what you see was you differentiate polynomial, they decrease in degree, right? For example, differentiate, uh, let's say x squared, you get 2x, and that's decrease in degree. Or actually, you see derivative of like sine x equals to cos x. But I claim that this also comes from differential equation, right? Why? Because we can write cosine x in terms of sine x, right? Is sine x plus pi or minus pi? Plus pi or minus pi? I think minus pi. Yes. Okay, so you shift your phases and you get back a sine function. Okay. Yeah. All right. So let's look at some examples here. So what's the differential equation? An equation that contains an unknown function and some of its derivative. First model you will see is called the exponential growth function model. If the rate of growth of population is proportional to its population, then we can write it like this. So this is proportional. Yeah, constant. Okay, constant time p. Okay, so it claims that this is a reasonable model, okay, especially for bacteria, okay, or animals under some ideal condition. And so meaning what? The change of your population with respect to time is linearly proportional to your population. Okay, does it make sense? Make sense. Okay. Yeah. Okay, so you assume that you will grow linearly. So we want to see that what kind of population, okay, what kind of function that can satisfy this equation. This is actually quite close to what we had before, right? For the e to the x, where we take k equals to 1. Okay, dp dt equals to p. Okay, where k equals to 1. But here k is random. Okay, random constant. So we will see what's the solution for this later. Okay, so in this case here, what's the independent variable here? Okay, can you recognize what the independent variable here? Or should I write a little bit more here? Okay, what's independent? Okay, time, yes, you cannot control. Okay, so time is independent. But then what is dependent on time? Your population. Okay, your population is depending on time. So you tell me after 1 year, how much you count, what's your population? After 2 years, does it increase or decrease? Okay. Like nowadays, what's the rate of birth in China? Increasing or decreasing? Decreasing, okay, because of your policy, right? One child policy. So it's important for the country to make a good policy, right? To keep your country running properly, right? So I think they are revising the policy, right? So now can you give birth to more than one child now? Three child. At most three. Okay, good. Okay, so uh, if don't act right, if the country don't act properly, then you can see that, for example, the country of Japan. Okay, actually Japan is an aging country as well. Okay. How about Singapore? How about Singapore? Singapore actually is a very relatively small country. Okay, it actually relies on migrants, yeah, immigrants. Okay, yeah. So they have to like offer a lot of maybe jobs or citizenship, okay, to uh, those skillful person. Even in Australia was like that. I was studying in Australia. Yeah, Australia is also an immigrant country. Okay, they rely on the immigrant to work for them. For example, after you graduate, right, you can apply for like the study and work visa. No, study and work visa, sorry. Work and travel visa. Work and travel visa. So you can go and, for example, you work part-time there, collecting the strawberry or what. Then uh, after your work time, you can use your money and go and travel. So it's like providing a labor for them because it's not that the strawberry uh will be how to say harvest every month, right? It's just a season. So it's a seasonal thing. Okay. Yeah. All right. So this is a life story. Okay. So dependent variable is the P, which is the number of individuals in the population. Population. Okay. So the next part is to straight away give you an solution, ask you to show there is a solution. Okay. Later on, we will try and figure out the solution just based on the differential equation. But now it asks you to show it is a solution. What does it mean? So it means that this PT here will satisfy the differential equation. Okay, so then we will let PT equals to A times e to the kt. Okay, then let's compute what's the derivative of this dpt dt. Okay, which is derivative of A times e to the kt. Okay, again, Okay, we start a new week again. I need to mention that the derivative is actually linear. Okay, so linear meaning you can pull out the constant first. Okay, and then do derivative. All right, so here e to the kt. K is another constant. So how do you differentiate here? Huh? Go back to your midterm material. How do you differentiate e to kt? What rule you use? Chain rule. Good. Okay. So actually you need to use chain rule. Shall I remind you? Okay. So for example, let W equal to KT and dW dt equals to K. Then what you get was A equals to D to the dW over dW and then dW over d, okay, which is A to the dW and then times K. So altogether you get A to the D to the sorry, A to the KD, sorry, A to the K, A times K, is it? Yeah, A times K, and then E to the KT. But we can write this more uh, sophisticated, so we can combine the A to the A times E to the KT, which is P. Okay, so we verify this differential equation. Does that make sense? Any question so far? No? Okay, good. I feel free to ask if you have any question. But then you can note that there's a constant A here, right? Okay, there's a constant A here. This K, the constant K here is fixed by your differential equation. But this A here is just random constant. Okay, so how we determine this constant is if you have an initial condition. Okay, then this constant could be determined. Right. So for example, let's say let P0 equals to 100. Then what you get was 100 equals to P0, which is A times E to the K times 0, which is just A. So A is 0. So then, hence, the solution that we need for this initial condition is 100 times E to the K. Okay, so how do you think about this? How do you think about this idea here? So this idea is when we show PT goes to A to the EKT, right? Really, you can think of them as a different function. Okay, different function with different A. So maybe A1, A2, A3, A4 like that. Okay, you can think of it as a different function or a path. Then once we set an initial condition, meaning you pick one of the curve, then this A will be determined. So if you pick an initial condition for A1, then this path will be determined. Okay, so for example, in this case here, we get PT equals to 100 equal KT, for example. Okay, so initial condition is like picking one of the solution. Okay, so this lead to something what we call the initial value problem. Okay, I tell you what happens at the initial time. Okay, all right. So any questions for this model here, exponential growth? Okay, so you can see that the derivative is relatively easy or it's just linear, but the solution becomes exponential. Okay, so if your change is linear, then your actual growth is exponential. Okay, your number will just so let me give you the idea of this picture here. So linear growth is like this. Okay, your growth is linear, but your actual number is going very fast, exponentially. I think this is why the China applied the one child policy back then. Okay. The derivative is very normal. I marry with you, I give child. I marry with you, I give child. But, but it is exponentially increased in number too much. Okay, so that's why they need to put this policy. But then now it dropped, so you need to revise the policy. Okay. Yeah, any questions so far? Okay, if no question, we'll go to the next model here. It's what we call the logistic model. Okay, so this logistic model here, can you see what's the difference with this logistic model with the exponential growth model here? There's an extra factor here. Okay, so there's an extra factor here. So what's this extra factor? 1 minus p over m. Okay, 1 minus p over m. What's m here? Okay, so k and m are some constant, but they call this m as a carrying capacity. Okay? Can you imagine when this factor equal to 0? When is this factor equal to 0? Exactly when p equals to m. Okay, exactly when p met the constant, it will be 0. And when is it 1? When population is relatively small, correspond to the carrying capacity. And if you're okay, so you learn limit, right? You learn limit, right? So imagine that this p is really small. Okay, when p is really small, this 1 minus p over m is just 1. So you go back to the previous case. Okay, but when your population grow as much, okay, then your derivative will approach to 0. Okay, so this is more realistic. This is what really happened in the real life. Do you see a YouTube video on the growing mice? Uh, uh, how to say? A lot of mouses, okay, in a place, and then see what happens. Did you see this experiment before? No? You want to see? Maybe let me find if I can find it. If we got time, I can show you. If no time, maybe I give you the link and then you can go back and watch. So what happened? Maybe I tell you what happened. So they grow maybe 10 mice or mouses together, and then these mouses grow until maybe 300 of them, and then suddenly they all die. There's a lot of reason behind dying because they have enough food. So the experimenter purposely give enough food, enough any facility to them, but they still die. It's very interesting experiment. Let me see if I can find it. If we got time, we can watch together. If not, I give you the. Or maybe we'll do it in the next hour. Okay, during the break I will find the video. Okay, so what we want to say is this is more realistic to our life. Okay, so let's see. So when p is small, okay, maybe I put a remark here. So actually the population level will level off when it approaches the carrying capacity. Maybe you might ask, what's the carrying capacity? So in reality, maybe you need to do some survey, okay, to talk about it. Imagine if you like living on Japan, on the or Singapore. So these are very small island, right? You could imagine that there should be some limit there, correct or not? Even if you put like every land a person, you cannot put too much people on one land, right? Either the land will sink um, or um, or there's not enough resources, right? Is this what happened in Jakarta? Anyone from Indonesia? Is it what happened to Jakarta? It's sinking? Yeah, too many people. Maybe also due to the construction problem, underground water stuff, right? Are you guys moving your capital now? I heard they are moving to Borneo. Is it true? EU plan. Okay. How long gonna happen? Not sure. Okay. Yeah. Right. So it's very important that we take care of our Mother Earth. All right. So when P small, what happened? So when P small, P over M is almost zero. Right? So maybe if you like, I can write like this: limit P to zero is equal to zero. Okay, more precise. So in this case here, what you get is dP over dt. It's just the case that we see before. Okay? Almost. But when P is greater than M, what could happen? Okay? When P is greater than M, then this means what? P over M is greater than 1, which implies that the factor 1 minus P over M actually is smaller than 0. It's negative. Okay. Could we have a negative growth? Just now what I told you, right? The mouses will die. Okay. You will have a negative growth. Okay. The mouses die. Okay. Is it dying? Would it die or not? Okay. This is almost like what happened in your career life. Okay. There's only 5 jobs I'm gonna offer to you, but there are like 10 applicants to apply. Okay, so there's limited space, very limited space. All right. So third thing we want to talk about is equilibrium solution. Okay, so what does it mean by equilibrium solution here? All right. There are actually two equilibrium solution. Okay, so one of them is PT equals 0. So meaning there's nothing for your population, or your population already um, met the carrying capacity. Can you see why are they called the equilibrium solution here? Can you see why? Equilibrium means what? It's like stable, no change. No change means what? Derivative is 0. So if they are constant, if their derivative will be 0. Okay. Okay, if there's you start with nothing, right? Don't so there's nothing to grow. Okay, but when PT goes to M, then the M, if you look at there, that factor actually is 0 as well. Okay, 0. Okay, so these are the two equilibrium solutions we talk about when derivative is 0. Okay. So this is what we call the first order differential equation, because the derivative here is just d over dt, only one derivative, and first order. Next, we will see something called the second order differential equation, which we refer to the mass spring system. Okay, we have this kind of second order differential equation, where we get m times d2x over dt squared might equal to minus kx. So this is actually Hooke's law, right? Okay, so Hooke's law saying that f equals to minus x. Okay, so when you pull down the the spring will automatically will move in the other direction to restore its position. So that force what we call the what's the force? Elastic force? No. What's the name of that force? I didn't learn physics for a long time. What's that force? What's the force that's stored in spring? Sorry. What's the force? Huh? Chinese says what? What's the name of the Chinese? Maybe I can recall. The spring. Kali. So in English, don't know. Anyone from English background or physics? What's this force name? For spring. Yeah, Hooke's law is the law that this force will follows, right? But what's the name of this force? Like gravitational force. Uh, what else? What's that force? Yeah, what's the name? I also forgot. Yeah. Okay. So there's a force that that forces again this spring to restore its position, right? So when it go back, but it compressed too much, then it will try to push it back, and then slowly there's a damping procedure such that it will end. Okay, otherwise, if there's no damping, right, maybe it will just go up and down forever. Yeah, because in this world we have damping, we have air resistance, so that there's something that uh, reduce okay the force. Okay, otherwise this force will follow the Hooke's law, F equals to kx. Okay. This kind of law is very standard in physics. So what physicists do was they measure the x, and then they measure the force, and then they plot it out, and then they fit the graph, and then it turns out that to be linear, very straightforward graph. Okay, so you just get F equals to minus kx. But what is this term here? Anyone can recognize what's this term? M times second derivative of displacement. A is acceleration. Okay, so actually this is the Newton's second law. F equals to ma. Okay, so here we equate these two laws together. Okay. So we think of the movement of the spring coming from Newton's second law. And then we combine with Hooke's law. Okay, so what's the relation? Okay, max here is fixed already. K is also fixed. This K will be depending on how stiff your spring is, right? Because yeah, how stiff your spring is. So here acceleration will be depending on your x. It depend on where you are in your displacement, how fast you can go. All right. So this is a second order, but I think in our course for now, right? We won't see these kind of examples. Mostly we will just see first order. Okay. Yeah, this not what we're gonna see for this course. All right. So how about try 9.1? Can you try this question? Try and verify that this is a solution for this differential equation. I give you 2 minutes.
Cannibalism, asexuality, and violence.
Wait, sorry, wait. Let me find a video. Hey, I suspect they really changed the projector and the sound much better. Okay, everyone got it? Is it straightforward? Or did you get stuck in calculation? All right, so then we will start with left-hand side. Right, side. So y prime plus tangent x times y. So what's our y here? So it's sine x cos x minus cos x prime times tangent x times sine x cos x minus cos x. Okay. But we know that tangent x is sine x over cos x. Okay. This will help us to cancel out stuff later. Right. So so you take derivative of this sum here. So it's linear, so you can take derivative of sine x and cos x. Sine x times cos x and cos x separately. But to differentiate sine x times cos x, you need products rule. Okay, so you need products rule. So what do you get here? So do you get minus sine square x plus cos square x here? Okay, and then the other term you get sine x. Maybe I split them up for you to see. For the other term, you can cancel out cos x. So you will just get sine x times sine x minus 1. Right. Okay. Yeah, so what's your goal? So your goal is cos square x. Okay, so can you get rid of the rest or not? So let's see. So the first term we get sine square x. And the other term obviously cos square x, then sine x. And then let's expand this. Sine square x minus sine x. Okay, so exactly we cancel out the sine square x and sine x. So we're left with cos square x. Okay, so we are done. So let's write the ST side here. Done. Right. Any question so far for this? Any question? Any question? So it satisfies the equation, the differential equation. It is the solution. Why is it differential equation? There's a derivative inside your equation. Kind of slow, sorry. Yeah. Okay, so there's a derivative. So this is a first order differential equation, DE, sometimes we call it. Or actually, it's an ODE, ordinary differential equation, because it's the normal, just one direction. Okay, any questions so far? Question? Any question, Felicia? Huh? Feel free to ask. Your question can follow? Can follow? Okay. I think we got time. So maybe after the break, I can show you the videos. Yeah, I think we can watch these 20 minutes videos. Can chill a bit, close to the end already. Okay. All right. So let's break. Let's break until 11:02.
Oh, we get started.
你们是第几组？啊，八，第八。Yes. About what? Result? Yeah, we will discuss on Friday. Yeah. Yeah. So you can see your test paper. Hmm. Elastic force sounds like it, I think. Elastic force. Yeah, should be elastic force. Yeah.
Work with the innate advice continuing to thrive well beyond what Friday, but
How little we know about rats.
early 70s, the subject was published in the national magazine Scientific American, and the experiments themselves were largely taken as apocalyptic importance. In a post-war United States, scholar Thomas Robert, these fears were here by Baltimore. The gatherers want for nothing, unquote.
Okay, I will take the attendance first.雅婷 here, not her,雅婷. 雅婷。陈凡 yeah. 伟业 yeah. 洪亮西河乐天瑞阳若实石曼一南玉涛一泽立文瑞妍泽汉嘉来嘉诚嘉怡齐军黄奇军黄奇军黄奇军黄一清一清 not here 黄一清齐军一清 not here 季敬义相思一林冰珍嘉叹 yes 浩云文琪汉祥俊杰万达新月玉恒一田冰城浩然Desmond Tommy 雄一英杰Gopagani okay Arthur Jose Hisham Daniel Madia here Daniel not here Aaron Aaron Brandon Alicia Gunakanti here okay Margaret here Javed here quite early saw you Gabriel not here Jeffrey Purity yes. Okay, maybe we study a little bit more, then we can watch the video together later. Okay, let's do one more and then we'll watch movie. Okay. So next up, we want to talk about the idea of a different curve here. So let's look at this partial first order differential equation here. So if you realize, right, our function actually could be written in two variable. Okay, so what do we mean by that? Well, so for example, let's say d over d. Okay, good. So, well, I mean, we just directly look at this question here is better. Okay, just look at this example. Y prime equals to x plus y. So we are written dy over dx with respect to x and y. Okay, respect to x and y. So with respect to x and y, right, we view x and y separately. Okay, so this y here is no longer depending on x only. Okay, So what we do is we view them as a separate variable here. So what we can do is for every point in R2, XY, we can plug in the value, right? We can plug in the value. So for example, let's look at the 1, 1 here. Okay, let's look at the point 1, 1 here. Okay, so look at the point 1, 1. So if you plug in 1, 1 into your derivative, what do you get? Actually, you get 2. So gradient is 2. How does the linear line looks like when gradient is 2? It's going from the third quadrant to the first quadrant, right? This graph here. So let's say this is U and V. So this is U equals to 2, V equals to 2U. Okay, so you can see that this line direction here is going upward. Make sense? Okay, maybe let's test one more. So this one going downward, right? So what do you think the gradient is? Negative? Okay, so let's try. Is it negative or not? So, well, can you roughly guess what's the point here? So this is maybe -1 and 0.1, 0.5. Okay, so let's try. So y prime of -1 and 0.5. Is it negative or not? So negative plus 0.5, what do you get? Negative half. Okay, so that's why the direction of this curve here is coming from second quadrant to the fourth quadrant. So it's this direction. Okay, negative gradient. Make sense? Okay. So in this case here, you can try and plot for every point. So what's the gradient? Is it positive? Is it negative? Is it zero? Horizontal? Okay. Does it make sense? Okay. So can you see that why this is more steep? Huh? Why is this more steep? Meaning the gradient is much larger. Okay, it's much larger. So that's why it approach to the vertical line. And then this one approach to zero, right? Almost zero here. Why is it almost zero here? These points are like -3 plus 3, like that. Okay. -3 plus 3 is what? 0. So the gradient is 0. What line have gradient 0? The horizontal line. Okay, so this is how we plot out this curve here. Okay, make sense? Okay. So then what? So imagine you are a particle. Okay. Imagine you are a particle. Okay. So this thing, what we call a direction field, right? Is like a wind. Okay, so the wind will blow flowing along this direction. So for example, if I put a ball here, what do you think could happen? Okay, so it will follow this direction field. Okay, for example, like go along with this direction field here. Okay. So for example, if you put a ball here, maybe it will go along the direction field. So maybe if you put a straight ball here, it just follow this direction field. Okay, can you imagine? Can you imagine what's this doing here? Can you imagine? Does it make sense? If doesn't make sense, you can let me know. Okay, so at every point there's a direction coming from the gradient. Okay. So do you still remember last time we draw a curve based on gradient? So once you have the gradient, then you will somehow know how your curve looks like. Do you remember? We can construct the curve from tangent line. Okay, this is what happens here. Okay, so you should imagine I have a ball starting here. Okay, I will move along this tangent line that trace out the curve. Okay, now this curve is what we call a solution curve. Okay, it's just a function again. Does that make sense? Okay, we can construct our curve using our tangent line. Still remember or not? The concave up, concave down, and the maximum, minimum. These are found from the tangent, right? The derivative in particular. So for example, this question here asks you to say, let's say I want to start with y0 equals 0. Okay, I start from this point here. So what's my curve? What happened to my curve? So this curve will like move out like that, right? Move out. And then in the other direction, move into here, for example. Okay, follow the direction. How about, so this is A. So how about, let me show the other one. How about B? Okay, let's start with B. So B starting point is when x equals 0, y equals to 3. So your starting point is around here. Okay, so where can this ball flow? Maybe out here. And then go sink into the same place again. Right. This is B. How about C? So C start with y0 equals negative 4 like that. Okay, so if you follow this graph here, maybe just okay, makes sense so far. Okay, so to be precise, maybe you need to draw even more direction for you. Okay, but roughly, this is the solution. Okay, so you can see that all of them could start from this middle part. So you can see that all of them sink to this tangent, that's this diagonal line. Okay, so far, so far. So this is we don't really go very deep into this. This is roughly idea, yeah, rough idea. Okay, so without solving the partial differential equation, right? There's some method called the Euler's method, right? Which we can use to approximate your solution curve. Okay, let's say we just only know how to draw the linear line. Okay, let's say we just only know how to draw a linear line. Then what we do was like what we did just now, no? We are like reconstructing the curve based on this little small tangent here. Okay, so if you just look at the tangent line at the starting point here, well, you should think that it would deviate a lot from your solution curve. It could be, right? It could deviate a lot. Okay, but what you do is you chop it up. Okay, you chop it up to the next second. See what's the tangent line here. What's the tangent direction here? And then you add up. You add this direction. Okay, so that it is closer to your solution curve. Okay? And then you imagine that you can split up again like a Riemann sum. Okay, you can split up this time interval here even smaller and smaller and smaller and smaller so that you can really get all the tangent vector or tangent line on your curve. Okay, approximate better. Okay, this is exactly what we did just now. We pick one point and see what's the tangent. Next point, what's the tangent? Next point, what's the tangent? So if you want to make this more precise, then you need to get more direction so that you can approximate the actual solution better. Okay, so this is what we call the Euler's method. Okay, so this formula is a bit crazy. A bit crazy. How to read this formula here? Let me see. How do we read this? Uh, uh, Maybe we don't read this and then I show you what we have to do using the uh, examples. Okay. So before we go to example, maybe we need to see what's inside the formula first, and then later we'll see how to use it. Okay. So first you have the initial problem y prime equals to fx of xy, so some function of xy. Then you know where your function starting. This is what we exactly started with just now. Okay, so just now was example y prime equals to x plus y, and then maybe y0 equals 0, right? One of the example. And then now we take the step size. So what step size here? So this is like the interval inside the Riemann sum. Okay, depend on how small you want to take. So for example, this step size is 0.5, but this step size is 0.5. Okay, so you increase by little and little. And then the claim is how to get the next point. Okay, how to get the next point. So from the first point, how to get the next point. From the first point, how to get the next point. Well, the idea is very simple. Okay, the idea is very simple. So you just look at this triangle here. Okay, you just look at this triangle here. So your yn minus 1 over the step size, okay, actually this is equivalent to what? This is just equivalent to xn minus 1. Okay. Then this should be your derivative. Right or not? This is the gradient, what we call gradient last time. Change in y over change in x. Okay, so this is very straightforward idea. Okay, although we write it like in a form that maybe you cannot recognize. Okay, so really it's just change of y over change of x. But your change of x already fixed. I want the fixed 0.5 or 0 each time increase. Okay, and then this f here actually is the derivative, the gradient. Okay, make sense? Well, so should we try one examples? Okay. So just now I just draw it for you, right? It's not very precise. But now let's calculate what's really happening here. Okay, so it's the same examples. Okay, same direction field we get. Y0 equals to 1. Do we have these examples? No. Okay. So our guess is like this. So let's see where is Y0 equals to 1. So we should start here. Okay, so our guess is this. So let's compute whether we get this curve or not. Roughly. Okay, we cannot get the exact one. So let's see. Okay, so the step size is 0.1. By 0.1, we need to update our gradient. Okay, by 0.1, we need to update our gradient. So let's compute a few of them. Okay, so let step size h equals 0.1. And then x naught equals 0, you start with x naught equals 0, and then y naught equals to 1. And our derivative is x plus y. So, okay, we do it step by step. So, y1 equals to y0 plus h of f of s0, y0. Okay, so what do we get here? So, y0 is 1, and then step size is 0.1, and then f, the derivative is just 0 plus 1. Okay. So what do you get? 1. So let's compare y2. So following the formula, okay. So if you notice the formula to get y2, you take the previous y1 plus step size times the time what? Time the derivative happen at x1, y1. So you continue there. Okay. Does it make sense? So look at this picture here. If I want to figure out this point here, okay. If I want to figure out this point, I take the point, the previous y, okay, and then I look at the gradient here, and then I add up. Okay, I add up the contribution from this gradient, the line of this gradient. Okay, so what do I get? 1.1 plus 0.1, step size is fixed, and then the formula of f is just x plus y. So you use the previous xy to compute. So you get 1.32. Okay. And then for example, y3, okay, maybe you tell me what's the formula here? Y3 equals what? Y3 equals what? Tell me the formula. Y3 equals what? Even maybe. Y3 equals what? Y2 plus 8 times 5 of x2, y3. Okay, so you take the gradient at s2, y2, and then you draw the tangent line. You draw a tangent line, and then you check what is y3. Okay. So this computation is very straightforward. Straightforward, so that you get, what do you get? Maybe you compute. Tell me the answer. See you can get a right answer. Try and compute. Any question? Any question. Any solution? What do you get? Jason, you got any solution? Hmm? Not yet. 1.362. Okay, how do you get it? 1.22 plus 0.1 times 0.2 plus 1.22. Yeah, that's it. Okay, so then you can go back to your graph here. Okay, maybe let's copy this. How can I screenshot it? Yeah, that's a screenshot. Good. Okay, let's verify this. Is it true or not? Is it close to what we draw here? Give me the photo. Good. Okay, so let's check it. You shouldn't scale it too much. Okay, so let's check. So what when when what when x1 what's s1? Oh yeah, sure. Okay, so we need to figure out what's s1, x2, and x3, right? Okay, so x1 is what? X1 is s0 plus 0.1. So which means it is uh, 0 plus 0.1, which is 0.1. X2, x1 plus 0.1, which is 0.1 plus 0.1, which is 0.2. So I think you should know that x3 is 0.3 because it's 0.2 plus 0.1. Okay, so let's check on these points. 0.1, 0.2, 0.3. Very small, super small. Okay, very small. So maybe somewhere here, 0.1, 0.2, 0.3. Okay, actually too far already because half is around here, right? So this is half. So 0.1, 2, 3, 4 like that. Okay. So when 0.1, what do we get? 1.1. Okay, somewhere above here. Okay, somewhere above 1.1. And then when it is 0.2, you get 1.22. So a bit up, bit further. So maybe we should draw a little bit upward like that. So maybe okay, let me do the correction. Maybe need to go a little bit up. Maybe here, 1.22. And then 0.3, 1.32. Or maybe go even further, 1.3. Maybe then you continue like that. But even this is not precise, right? Because you can make it more precise, like 0.05, 0.001. Okay, so could the actual curve could be looking somewhere like this. Okay, any question so far? Question? Okay, but anyhow, it's still following the general pattern is correct. So we are going up and following the direction of the tangent. Just that how precise we are depend on the how small the step size you take in your Euler method. But the general pattern is correct. You're going up because you're following the direction of your direction. Any questions so far? Any question? Okay, so I mean, Maybe one thing you want to remember from this class is today class was you get this derivative, right? Okay, if you check on xy, then this will give you a gradient, and this gradient will plot out the direction. Okay, any question so far? Any question? Question so far? If no question, Friday, I want all the leaders to report to me what's your progress on your presentation. Okay. So now maybe we can watch some video on this mouse utopia experiment. So one of the caption, maybe I can show you one of the caption of this video, right? Is I cannot find it. Yeah. So one of the videos say that why paradise led to extinction. Okay. So in this experiment, the mouses are provided ample food, ample shelter, okay, ample water, but they still die in the end. So don't complain that your life is hard. The life is meant to be hard, otherwise you will die. Okay. Okay. So you meant to work hard, otherwise you will die. So let's see how these mouse die. Uh, Fortunately, I found a video that have a Chinese caption. So maybe I'll put the caption on. For those who are English speaking, maybe you can listen. For those Mandarin people, you can read the caption if you cannot catch up with the video. Okay, so enjoy.
Of the strange research to come out of mid-1800s America, there is little with a legacy as enduring or as terrifying as the mouse utopia experiments. Taking place throughout the 50s, 60s, and early 70s, the grim fate of the subjects was published in the national magazine Scientific American, and the experiments themselves were largely taken as apocalyptic portents. In a post-war United States, the language used to describe the results, such as behavior sync, became synonymous with fears of an overpopulated world and violent, deviant behavior in cities. Today, they are preserved within fiction, such as Channel 4's conspiracy thriller Utopia and the classic animated movie The Secret of Nim. So, what were the Mouse Utopia experiments? Shortly after World War II, a group known collectively as the environmentalists were making a large push to prevent environmental degradation as well as overexploitation of the planet's renewable resources. Among these people were a group specifically known as the Neo-Malthusians, a term referring to the 18th and 19th century English scholar Thomas Robert Malthus. Malthus proposed that while the world's population may increase exponentially, food production can only increase linearly, leading to an eventual subsistence level existence for the human race that became known as the Malthusian catastrophe. While advancements such as the Green Revolution saw that this didn't come about, the Neo-Malthusians acknowledged his concerns about overpopulation and feared that this pattern would result in the collapse of civilization or, at best, have extreme adverse effects. These fears were given a platform in writing of the time, especially in works such as William Folk's Road to Survival in 1948, and perhaps most famously, Silent Spring by Rachel Carson in 1962. Before the movement's explosion of popularity in the 50s and 60s, however, researchers had already begun work investigating the effects of population growth, and among them was a man named John B. Calhoun. Born in 1917, Calhoun took an early interest in science, specifically ornithology, publishing his first paper on birds when he was 15. But over time, his interest would change. By the time he received his PhD, his focus had turned to ethology, the study of animal behavior. When his education was concluded, he moved with his family to Towson, Maryland, to begin research at Johns Hopkins University in nearby Baltimore, but the research itself would be conducted much closer to home. In 1947, shortly after he arrived, he approached his neighbor about using some of their neglected property for an experiment. The scope would be massive, and according to Calhoun, his neighbor probably didn't expect such a scale when they agreed to let him use the forested area. Taking over a quarter of an acre, Calhoun constructed a massive habitat, complete with food, water, ample shelter, and protection from predators, with the only limiting condition being their restriction to the quarter-acre living space. He affectionately provided his enclosure a name, Rat City. Unfortunately, no publicly available images of Rat City exist. Calhoun was very familiar with Norway rats, having performed research on them for his doctorate, and he estimated that Rat City could sustain approximately 5,000 individuals, though if they reached this number, the population density would be tight. He began by placing 5 pregnant females in the enclosure, providing ample genetic diversity, and soon the population was increasing exponentially. But then something surprising happened. Rather than the population increasing to fill the space of the enclosure, it quickly leveled off at 150 members. He also noted some behavioral peculiarities. Despite the large size of Rat City, the residents seemed to gather around just a few places, forming social groups of 12 and limiting themselves to specific feeding locations. He would conclude the experiment after 2 years and 4 months, during which the population never grew over 200. Careful observation revealed the cause: high infant mortality. For some reason, as the experiment progressed and the population increased, the mothers were not caring for their young properly, leading to most of them dying before reaching maturity. Kuhn had his theories as to why this was, but to prove them, he would need more data. In 1954, about 5 years after his initial experiment concluded, he was hired by the National Institute of Mental Health, often shortened to NIM. Within the laboratory of psychology, Calhoun was given ample resources to continue his work. With a team, he began feverishly designing and constructing habitats, sometimes referred to as universes, where he performed numerous smaller scale and more controlled versions of his original rat study on a domesticated strain of albino Norway rat. These rats would want for nothing. All physical needs for a healthy rat lifestyle would be provided for them, including food, water, climate control, and nesting material. Calhoun spent 8 years perfecting his enclosures and methods until finally, in February of 1962, an article of his writing was published in the magazine Scientific American. The article was entitled Population Density and Social Pathology. His opening paragraph ominously reads so, quote, "In the celebrated thesis of Thomas Malthus, vice and misery impose the ultimate natural limit on the growth of populations. Students of the subject have given most of their attention to misery, that is, to predation, disease, and food supply as forces that operate to adjust the size of a population to its environment. But what of vice? Setting aside the moral burden of this word, what are the effects of the social behavior of a species on population growth, and of population density on social behavior?" Unquote. To answer this question, he cited 6 of his experiments in particular, all with similar composition and concerningly similar results. The design of these habitats was simple. The layout was a rectangle measuring 10 feet by 14 feet, divided into 4 equal sections by electric fences. 3 of these fences sported bridges over which the rats could climb, while one fence lacked such a bridge, essentially creating one long space that wrapped in on itself. Each section was equipped similarly with a food hopper, water, and nesting areas accessible by spiral staircases. But Calhoun, leveraging his experience with the rats, made special changes to encourage specific behaviors. He enticed the rats to use one of the center pens by making the spiral staircase to that pen's living spaces shorter than the others, though he admits this was a comparatively small factor. But the more insidious change was to their food supply. In half of the experiments, Calhoun supplied powdered food, but in the other half, he placed feeders of his own design, consisting of hard pellets behind a wire mesh. Half of his experiments began with 32 mice, the other half with 56, of evenly male and female composition, and all having just reached maturity. Calhoun estimated that approximately 40 rats could comfortably be housed in these enclosures, but he would allow these populations to increase to 80 before he would cull them. Almost immediately after introduction, things began to go awry. The females, unsurprisingly, spread themselves out somewhat evenly through the pens, but after the males jockeyed for dominance and those of highest rank were determined, they began to distribute themselves strangely. Less dominant male rats will typically awaken earlier and begin to wander and forage for food, and due to the design of the pen, this meant that they usually would end up in the center sections to eat. During this time, the dominant males of the outer pens would wake up and begin guarding their respective territories. Since there was only one entrance ramp to either end, the dominant males of either pen would bar the return of the less dominant males, forcing the male population to clump in the center pens, while the dominant end males protected what came to be their harems. Only a few other differential males were allowed to remain. These few remaining males began exhibiting odd behavior. Though they would spend most of their time in the burrows with the females, hiding away from the dominant male, they would never attempt to mate with any of them. Instead, perplexingly, they would try to mate with the dominant male, and even more perplexing, the dominant male would not fight these attempts. At the same time as this was happening, the effect of Calhoun's special feeders was taking hold. Since procuring food was such a lengthy process at the hard food feeders, it was common for one rat to join another while in the process of feeding. By this method, the rats slowly became conditioned to eating in the company of other rats until, eventually, the rats would refuse to eat unless another rat was present. Since more rats tended to be in the center pens, this behavior meant that, over time, more and more rats made their way there, further condensing them. This heightened the proximity of an already cramped population. In the experiments with the powdered food, this effect was far less pronounced. With these factors combined, Calhoun noted what he called a behavioral sink, or an increase in pathological activity in the rats due to the stress involved in such high population density. For the females, the behavioral sink manifested in reduced capacity for nest building and young rearing. Infant rats are extremely dependent upon their mothers for nearly all things. However, under the effects of the behavioral sink, the mothers would often be interrupted in their nest building practices to engage in some other social activity. As time wore on, this led to sparser nests which could not house the young properly. If a mother decided to move her litter, she often would only move some of them or scatter them about the pen in separate locations. What's more, when female rats are ready to mate, the males can sense it, and the enclosed space meant that a female could not escape the continuous advances of the males during these periods. Even when they would enter their nests for a reprieve, they would be followed in and harrowed. These factors together resulted in an extremely high infant mortality rate, in one case reaching 96%. For the males, this manifested in different ways. The dominant males would occasionally lash out in violence against the other members of the pen, including infants, often biting and wounding with tails. Among the lower class males were three groups. The first he described as the homosexuals, which he immediately corrects as pansexuals, who would not compete for status, but would often attempt to mate with any other rat, regardless of gender or age. Much like in the end pens, these advances went unchallenged. The second group he described as somnambulists, who moved slowly through the pen without interacting with other individuals in any fashion, and the other rats in turn ignored them, except in rare circumstances. These rats externally he described as fat, sleek, and healthy looking. But to him, the strangest group was the third, which he named the probers. These rats were hyperactive, hypersexual, and pansexual. Despite violence from the dominant males, they would viciously pursue females in heat, eschewing any sort of courtship ritual and following them into their burrows to mate. Later on in the experiments, they would often find the corpses of the improperly cared for young, which they would cannibalize. In time, one of Calhoun's assistants would publicly describe these pens as hell. At this point, Calhoun ended the experiments, but he predicted that these pathological changes would have eventually led to the deaths of the colonies. At their conclusion, he would take the four healthiest males and females and allow them to breed, but their behavior had been so inexorably altered that none of their pups survived beyond weaning. This short article enraptured the U.S. audience, and the effects on both the scientific world and popular culture were immediate. People began to relate Calhoun's rat experiments to modern city life, and in an era where fear of social deviance was reaching an extreme high, it was largely seen as a reflection of the current time and where society could be heading. egged on by Calhoun's provocative language and allegorical design of its test environment, made to look like a city. Population density quickly became a common topic. Psychologist Carl Rogers, in his work Some Social Issues Which Concern Me, stated that, quote, the resemblance to human behavior is frightening. In humans, we see poor family relationships, the lack of caring, the complete alienation, the magnetic attraction of overcrowding, the lack of involvement, which is so great that it permits people to watch a long, drawn-out murder without so much as calling the police. Perhaps all city dwellers are inhabitants of a behavioral sink. Unquote. Soon after, studies of dense urban environments were conducted to see if these effects translated directly to humans, but what they found was inconclusive and unsatisfying. Despite the suggestions of Calhoun's rats, humans in cities reacted differently or sometimes opposite the manner that researchers expected, depending on the location. No matter how they tried, no evidence of a widespread behavioral sink could be found in urban areas. But this did not dissuade Calhoun. Even as others explored the problem of overcrowding, Calhoun frantically continued his research. Now a celebrated success and emboldened by the public acceptance of his ideas, he resumed his work at NIM on an even larger scale, though again away from the public eye. He spent his time on new subjects as he continued to perfect his enclosures and experiments until finally, after 11 years, Calhoun revealed his magnum opus through an article he entitled Death Squared, which was published in the journal Proceedings of the Royal Society of Medicine in January of 1973. The lengthy opening to this article was undeniably apocalyptic. Calhoun wrote, I shall largely speak of mice, but my thoughts are on man, on healing, on life and its evolution. Threatening life and evolution are the two deaths, death of the spirit and death of the body. Evolution, in terms of ancient wisdom, is the acquisition of access to the tree of life. Unquote. He goes on to heavily reference revelations and of the riders of the apocalypse, using them to proclaim that the Hippocratic oath applies not only to the body, but to the spirit. After this dramatic introduction, he described his test. For the most part, these new experiments were similar to his 1963 trials, including unlimited access to food and water, protection from the elements and predators, and safeguards against disease. Many parts, however, were drastically altered. As Calhoun mentions in his introduction, the Norway rats used in his first publicized experiments were replaced with albino house mice, which were taken from a breeding group from the National Institutes of Health made specifically to prevent communicable disease. To fit his new subjects, Calhoun had designed an entirely new enclosure. This version was much more vertical, with 16 wall-mounted housing areas for the rats at the tops of long metal tubes, which Calhoun called walk-up apartments. At the bottom of each apartment was a virtually unlimited supply of food, water, and nesting material. With the space provided, Calhoun estimated that it could potentially hold 3,840 mice. He named this enclosure Universe 25. Calhoun's methods also had changed. Rather than instituting population controls, he would interfere far less. His plan was to place 8 mice in the enclosure, 4 male and 4 female, and simply watch and wait. Calhoun observed 4 distinct phases in the ensuing experiment. Phase A was predictable, constituting the time period before the first new mice were born, which ended up being 104 days. For the mice, these days were, quote, marked by considerable social turmoil. After the social order was established and the first brood was born, the population began Phase B, which Calhoun named the exploitation phase. During this time, the mice doubled in number every 55 days as new young grew to maturity and had their own young. This doubling continued until day 315, after which the doubling rate slowed to a rate of 145 days, nearly 3 times as long. By this point, the different broods had clumped into one side of the pen, exhibiting the same sort of clumping as the Norway rats, but this time without any coaxing from Calhoun's designs. This change in the rate of procreation marked Phase C, which Calhoun labeled as the stagnation phase. This is when the most notable events occurred, and they eerily mirrored Calhoun's rat experiments. In a natural setting, those mice which find no social niche will leave the colony, but in this experiment, emigration was impossible, and so those forced to remain withdrew from society. These dejected males formed a large pool in the center of the enclosure. They quickly became characterized by both their inactivity and their many scars and wounds. Occasionally, they would grow agitated and attack one another, and with nowhere to retreat, the recipient of these attacks would simply lay still and endure the assault. The outcast females, rather than joining them, would retreat to the highest apartments and live quietly among one another. It was during this time that the behavioral sink manifested, with mice gathering around specific food hoppers in large numbers, while others remained almost entirely untouched, showing how, again, the need for social interaction had become so intertwined with the need for food that the former had overtaken the latter. The males who had won the initial fights also were placed under extreme stress. As more and more mice reached maturity from within and without, the leaders of the social groups continually had to patrol and defend their territory. Eventually, they reached the point of exhaustion and could not defend the females within their group. These females were therefore forced to defend the nest themselves, even when nursing their young, leading to generalized aggressive behavior. This aggression would inevitably be misdirected onto their young, who would be wounded by their mothers and forced to leave the nest before they were finished weaning. Much like the rats, the mother mice would also forget some of their young when moving from one nesting site to another. Due to the added stress of defending their territory, sometimes the mothers would reabsorb unborn mice in the womb, further reducing the fertility rates. Calhoun writes, for all practical purposes, there had been a death of societal organization by the end of Phase C. Finally, there was Phase D, which Calhoun entitled the death phase. This phase was characterized largely by an entire generation of young who had been rejected by their mothers early and forced to leave the nest, and they were therefore unable to exhibit normal social behavior. This manifested in numerous ways. The females of this generation had far fewer children, and those that did have children lacked the maternal instincts necessary to raise them beyond weaning. Calhoun goes on to describe the males of this generation. Quote, male counterparts to these non-reproducing females were soon dubbed the beautiful ones. They never engaged in sexual approaches toward females, and they never engaged in fighting, and so they had no wound or scar tissue. Thus, their pelage remained in excellent condition. Their behavioral repertoire became largely confined to eating, drinking, sleeping, and grooming, none of which carried any social implication beyond that represented by contiguity of bodies. Unquote. As the last mice with reproductive instincts aged beyond their fertility, Calhoun declared that the last male would die around day 1780 of the experiment, effectively rendering the colony dead as it would be unable to produce any more young. His present tense language implied that, when the article was published, the colony was still technically alive, though its final fate was practically sealed. Calhoun closed his article with a call to action. For an animal so complex as man, there is no logical reason why a comparable sequence of events should not also lead to species extinction. If opportunities for role fulfillment fall far short of the demand by those capable of fulfilling roles and having expectancies to do so, only violence and disruption of social organization can follow. Individuals born under these circumstances will be so out of touch with reality as to be incapable even of alienation. Their most complex behaviors will become fragmented. Acquisition, creation, and utilization of ideas appropriate for life in a post-industrial, cultural, conceptual, technological society will have been blocked. Just as biological generativity in the mouse involved this species' most complex behaviors, so does ideational generativity for man. Loss of these respective complex behaviors means death of the species. But even as Calhoun was performing his research on mice, others had been at work applying his theories to humans. By this point, researchers had moved to more specific locations of overcrowding rather than the generalized location of cities, testing the effects on students in dormitories and patients at hospitals. But the most fruitful example they discovered was in prisons. Paul Paulus from the University of Texas wrote that prisons were the perfect place for this sort of study, describing the social interaction between inmates as intense, prolonged, inescapable, and realistic. The prison and the study also offer the closest analog to Calhoun's rat experiments, since the prisoners could not escape the company of others, even in their communal cells. There, they found connections between over-socialization and suicide, violence, psychopathy, and stress. After such studies, environmental psychologists began to discover the problem. They identified two different kinds of density, physical density and social density. Physical density was the amount of space per person, while social density was the number of individuals occupying space. They found that social density was the much more important factor, as individuals in high social density were unable to control their interactions with others. Based on this research, human environments could be designed to at least partially mitigate these issues, allowing those living within them the privacy they needed to maintain social interaction. Outside of scientific discourse, Calhoun's rhetoric has maintained its strength through the years, with different groups of all political persuasions bending his results to support their views on social degradation, however they may define it. Among more scholarly sources, Calhoun has been both lauded and criticized for his work. Those who support him cite his forward thinking about overpopulation, while those who deride him cite his misrepresentation of the actual social problems within cities, guiding discourse away from the true causes of societal discord. But no matter what those in the modern day think of his research, his influence on the way America views its cities is undeniable.
Okay, so if you are interested in this, you can search more. It's called Universe 25. So if you look at this M here, right, just now, he mentioned that there's one time the M is 120 or no exiting 200 mices, right? And then until he do the latest experiment. And final things I want to say, yeah, final things. So this as equilibrium solution, right, has to be these two. Do you know why? Because if you do the derivative, you get zero. But at the same time, this zero will satisfy the right hand side. Okay. If you try with any constant, it doesn't work. Because if it's not zero or m, it's just some random k, right? Or random n. This number here might not be zero, so it's not a solution. Okay, so it is a solution, equilibrium solution when PT is zero or you reach the carrying capacity, like what we had in the experiment. Okay, all right, we'll see you on Friday.